Hey guys, so today we want to discuss some gas diffusion models and how the thought process behind these models. So gas diffusion is something we did not discuss before, and we assumed that that didn't happen, as all the xenon trapped in the fuel would be assumed to cause bubble growth, as seen in our bubble growth equations. And this gave us an approximate upper limit to how much swelling would occur over time. Now this is great for designing a fuel pellet, okay, because you want to see how much spacing you need to give the fuel pellet to expand to expand while it's in the cladding. However, does all xenon get trapped like we assume? Does it all go into like growing bubbles, or being trapped in the, will it be trapped in the fuel matrix? What usually happens? Sometimes the gas will diffuse outside in the fuel pellet. The gas may diffuse outside here. And at other times, an atom undergoing fission will release a xenon close enough to the surface that you'll escape the fuel completely. For example, if an atom were to fission here, and xenon were to escape like this, it will not get lodged into the fuel, but it will instead be launched into the cladding. If let's say this is a xenon atom that's coming off a uranium atom, it will launch straight into the cladding here, if it is relatively close to the surface. So as shown in page 299 of Professor Olander's book, this effect where the xenon escapes directly via direct fission, and it becomes a swift ion and escapes the fuel pellet before it is stopped. This effect may not be as important for fission gas release as compared to diffusion. So I'll just call it the direct escape. There's a proper name for that. Direct escape, not so important as compared to diffusion. So direct escape is not as important compared to diffusion. Excuse me. So in this video, we want to discuss more about the diffusion part. And diffusion itself is a very complicated thing. Models. So we want to talk about diffusion models. And diffusion itself is very complicated, because if you want to talk about diffusion from the fuel, we should know that each fuel pellet is made up of many grains, and each grain is separated by grain boundaries. So these grain boundaries are very small cracks. They may be attached to some larger cracks in the fuel, because when the fuel is being burned, there will be cracks. And if the if the gas actually diffuses to the grain boundary, one may think that, oh, the cracks will link up to like these big cracks caused by the thermal expansion, and there you go, the gas would have escaped through here. But that's not always true, because sometimes the gas can nucleate at the grain boundaries, like so. Okay, so furthermore, if you want to describe all this mathematically, that was very difficult. And the other thing that complicates things is that the fuel itself is not homogeneous. These grains, they are not of the same shape, and they're not of the same size, and that complicates diffusion models. So release from the fuel pellet is kind of complicated, but we want to make it simple. So how can we have a simple model? So we want a simplified model. So for the sake of calculating fission gas release via grain boundaries through diffusion, we assume that the fuel pellet is instead made of individual spheres of equivalent size. So I'll go through a few mathematical models based on this assumption. Now suppose that each grain is now represented by a sphere, and the surface to volume ratio is as such. So the surface that is available here of each sphere that's available for the gas to escape, that is 4 pi, let's call this radius A, 4 pi A squared over 4 over third pi A cubed. Okay, and that will give you 3 over A. So that is the surface to volume ratio. So I'm using the same nomenclature as Professor Olander, his book, okay, as subscript T. And this surface area here can be measured through gas adsorption techniques, something similar to the Brunauer-Emmett teller, BET. BET, yeah. If you're not sure what this is, you can go and see the video link I'm posting to introduce to you pictorially this concept. So the stuff I'm sharing here is on page 300 onwards of Professor Olander's book. And firstly, what are we interested in? We are interested in fractional release. Fractional release. So how much gas is in the sphere? So how much gas is in the sphere versus how much is released? So total gas in sphere and total gas released. So what's the total gas release? If we take into the account the diffusion, we'll have some surface area multiplied by the flux over time. So this is total gas release over time. So we have a 0 to T of J dt. Okay, that's a total flux release. Flux times area equals to the total amount released via diffusion. And we'll have some concentration, initial concentration times the volume. So this is assuming pure diffusion. Okay, this is a pure diffusion kind of equation. We don't assume there's any generation or anything like that. So we just assume that a fuel pellet has some fixed initial concentration, and then everything kind of diffuses up from there. So area to volume. So this is the surface to volume ratio. As we calculated just now, that is 3 over A. And we'll just need to evaluate this integral here. Okay, so how do we calculate flux based on the fractional release? So how do we calculate this J? So if we were to look, J equals to minus D dC dr. So this is the concentration gradient times the diffusion coefficient. This is Fick's first law. Okay, this is Fick's first law. Simply that the flux is related to the diffusion coefficient times concentration gradient. How do we then figure out the concentration gradient? Well, the concentration profile is done considering Fick's second law applied to a sphere. So Fick's second law is just a mass balance. If you want to think about it, it's derived from a mass balance. So the accumulation over time equals to d over 1 over r squared, diffusion coefficient, and then the differential del by del r squared into del c del r. I'm not going to derive it here, but this is merely Fick's second law for a sphere, spherical coordinates. fixed second law for spherical coordinates. So we have to solve this differential equation, partial differential equation, in order to get the concentration profile. Then we can calculate J, then we can find J over time. So we know that this concentration gradient, that will be a function of time, and that we will have to take into account. So we also ignore the recoil of fission products, i.e. the direct escape route kind of described earlier, and this is relatively negligible. So the other name I wanted to talk about, this is the direct escape. The more correct name is called recoil. The fission products kind of recoil off into the cladding. The more correct technical name. Anyway, so in this case we ignore the recoil of the fission products, and the direct escape route is negligible. Also, the fuel pellet is assumed not to be in a reactor, so there's no generation of fission gas. And also, the radioactive decay of the fission gas is neglected. So what next? We need some boundary conditions to start. So at t equals 0, so these are the boundary conditions. An initial condition. Okay, at t equals 0, C naught, C equals to C naught in the sphere. Everywhere, it's a homogeneous C naught distribution. So C naught is the concentration of the gas produced under irradiation prior to the diffusion. And the diffusion is allowed because of the high temperature, so it's kind of an annealing kind of thing. It's a heat treatment, sort of similar to annealing, but the purpose is to get the gas out. So at any time after t equals to t, so time equals to any kind of a time t. Okay, so or rather, let's put it this way: time equals 0, time equals to t. The concentration of the gas at the center of the sphere. So center of the sphere, R equals 0, C equals to finite. So there's not no infinite concentration or anything like that. So at time equals to t, at the radius, at the edge of the sphere, R equals to A, concentration of gas equals to 0. So concentration is 0, but that does not mean that the concentration gradient is 0. So after you solve via non-dimensionalization, and you do a few more like Laplace transforms, you can see the details on the page 300 to 301 of Professor Olander's book. I won't go into detail of the math, but at least you should know the assumptions as to understand why the math is the way it is. Okay, so most of the calculations deal with fractional gas release, so they account for the total flux over time. Okay, so after all these things, we find that the fractional release for this non-irradiating, this is just like pure gas diffusion. There's no nuclear process or nuclear fission going on. We will have this kind of fractional release. So F equals 6 over root pi of diffusion coefficient times time over the radius of the sphere, the radius of the hypothetical sphere squared. And since we don't know A, we can combine this and this into some empirical coefficient. So if you see equations in this form, don't be confused, because this d prime here equals to d over a square. So we can't actually measure a square, but we can just combine this into some diffusion coefficient and kind of like measure the gradient. So this will help us to represent the release of gas over time at some temperature. So plotting F versus this T to the power of half, the fractional release to the T to the power of half, we can find this d prime, and that helps us to fit it back into our model. Okay, so as to kind of like hopefully predict. Anyway, this is assuming a fixed amount is trapped and now is released by increasing the temperature uniformly, and usually this temperature is about 1000 Kelvin for this diffusion process to happen. How about fission gas release in the reactor situation? Now, if we were to account for production and decay, now the fixed second law, which is the mass balance, will be something like this. Well, this isn't exactly fixed second law, but this is a mass balance. Okay, so the yield of, let's say, a xenon, yxe into F, okay, times the diffusion in and out, minus lambda c, and this is the decay rate of the gas. Again, the same release formula is used. 3 over a c naught, integrate from 0 to t, j into dt. But in this case, c naught is replaced by y xenon f into t. Why? Because this is the total amount of fission gas available inside the fuel pellet. So this is what the expression will look like. Now, with more terms in this PDE, we will want to consider a few limiting cases for simplicity. So if we want to assume the special case of no decay, so if a case 1, no decay or negligible decay, neglect decay, so we repeat the similar procedure which we have before. So lambda c approaches to 0, and what we get is the following expression: f equals to 4 over root pi dt over a square to the power of half. Or alternatively, it will get something like this. So it's a d prime. Okay, this is the case 1. The other extreme is that the radioactive decay is very large. Large decay. So that means that the accumulation of gas is not possible after some time. So del C del T equals to 0. So essentially, we are assuming a steady state kind of a situation. So 0 equals to y f dot plus d over r squared del by del r squared del c del r minus lambda c. Okay, repeating similar assumption and procedure, again that will yield the following case. Okay. F equals to 3 d over lambda a squared to the power of half So notice that there's no more time constant, but it depends heavily upon the decay rate. And again, if we combine these two, 3 over root lambda d prime to the power half, that will be the what we will have. So this is useful for measuring short-lived products. So if the fractional release follows this kind of a pattern, we will know that short-lived products are escaping. This means that the fuel has cracked or failed to hold in the fission products. And using this to measure is useful for using this characteristic like release pattern is useful for signaling this sort of scenario. Now, one simplifying assumption was that the above assumes uniform temperature. So before, assume uniform. But in a reactor setting, the heat source is such that the temperature profile is not uniform. So remember, in the reactor itself, we were saying previously that the hottest part is in the center. So T is a function of temperature. T is a function of the radius, and also we know that since the diffusion coefficient d prime equals to a function of temperature, we'll have to take temperature into account. So this is the Arrhenius equation. So the temperature profile is as follows. So this is the T of the surface. This is the center temperature. This is T as a function of R. So this is a typical fuel pellet kind of temperature distribution. So this R is for the cylinder. This is not to be confused with A. A is the radius of the sphere. So if we were to take into account all this temperature variation and repeat the analysis, we can obtain some average diffusion coefficient called d bar prime. Okay, so d bar prime is here, and this is the average by temp of diffusion coefficient. Okay, and again, if we have d bar prime, then we can have this expression. Fractional release equals to 4 over root pi d bar prime T to the power half. So what is this d bar prime? Again, done through more calculus. This is page 303 of Professor Olander's book. Okay, d bar prime to the half equals to the following. Now this is very long. T star over 2 T naught minus Ts into E minus T star over T naught, okay, over T star by T naught, T star by T naught plus 1. Okay, so what are you seeing here? Well, first you might be asking what T star is. T star is E prime by 2k. So this is the Arrhenius equation. So E by k as seen here. The rest of the temperatures, they have their original meaning. So now we have accounted for temperature variations from center line to the surface, but we have not accounted for axial variation in the rod. So we will need this. So what this P is, this is P, power of the rod per unit length. Power of the rod per unit length. So we can do a similar average. So as per page 303 to 304 of Professor Olander's book, 4 over root pi. So this is F like double bar. The double bar prime t to the power half. Okay, so what is this d double bar? So again, we will have to do something like this. So this is after all the math, the solution is as follows. Z over 2 to Z over 2 d. This is the original d bar we were talking about, which was this. Okay, temperature dependent. Okay, so minus Z over 2 to Z over 2 PZ P naught dz. So what is this z here? Okay, so z is this height of the cylinder. So at the P0, it means P, the linear power at z equals 0. So that is directly in the center. The bottom is minus z over 2, at the top is z over 2. So you can imagine at the center, directly at the center, that is where the linear power the power density is the highest. So P of z is the power per unit length at any point of the axis over here. Okay, so all of this can be this Pz over P naught. It can be represented by a truncated like cosine function. So you want to see more details, that will be in Professor Olander's book. So for ultra radioactive fission gases, or rather a steady state case with the two temperature variations, we'll have things like this. Okay, with d double bar being the same. Nevertheless, despite all this math being taken into account, this model fails to predict fission gas release outside its data range, and this is known as the Booth model. So what we have been discussing is the Booth model. So that's one way of thinking about fission gas release. Now the weakness of this model is that it fails to predict fission gas release outside the data range. So this is very highly empirical. So it cannot predict gas release rates outside its data range. So what it means is that if let's say you have a gas release versus time or something like that, so if this is the data range, let's say there's this hypothetical linear plot, you cannot extrapolate. Sometimes the actual plot may be like that, and this is data we don't have. So that's the idea of what it means. So we can see that fission gas release is pretty complicated, and we need a lot of math to take into account for each effect, the radioactive decay, the production, the temperature variation, etc. So making lots of simplifying assumptions in this case, that kind of takes away the predictive ability of the model. But I mean, it makes modeling possible, but not very accurate. So I know this is quite a fair bit for one video, but it's just to illustrate to you how complicated modeling fission gas release is. Hopefully this helps you to know some of the thought processes involved. And there's plenty more to explore. But I'll stop for now. You can read more in Professor Olander's book in page 303 onwards. This is chapter 15, fission gas release. So thanks for watching this video. Okay. So in summary, we've asked the question a few videos back. So we want to close some of the loops. So how does fission gas release affect thermal conductivity? Qualitatively speaking, we know that as the bubbles grow, the fuel will swell. And as the fuel swells, as the fuel swells, the fuel cladding gap decreases. So normally there will be some spacing between the fuel and the cladding, but when it starts to expand, the gap decreases. So the conductivity will kind of increase. But within the fuel itself, because this was completely solid and this is a mixture of solid and gases, the conductivity actually decreases. So the gap conductivity increases because the gap has been decreasing because of the swelling, but fuel conductivity decreases. So how much? Sometimes it's very hard to experimentally determine that, and anything with bubbles and gases is generally quite hard to model. So the easiest approach is you have to experimentally measure. So one of these ways is through laser flash analysis. So okay, so basically they'll have a sample of fuel here. There'll be some infrared or some thermal sensor here. And then there'll be a pulse of laser being directed to the opposite side. A pulse of laser directed to the opposite side. And then the thermal sensor will see how long it takes for the temperature here to increase. And that will be telling of the thermal conductivity of this fuel element. How about gas release out of the fuel? As the fuel swells, the fuel cladding gap decreases, and the thermal conductivity between the fuel and the cladding increases. But when the xenon is released from the fuel, into this gap, which is also called the plenum, when the xenon is released here, it's released into an environment that's normally filled with helium. So as xenon begins to sort of mix with the helium, okay, so here's normally a helium gas. Now as the fission goes on, the xenon starts to mix with helium. What happens to the thermal conductivity? A xenon helium mixture versus helium. So this is the conductivity comparison. Well, the conductivity of this is much worse, or rather it's just worse, because xenon has a conductivity 26 times worse than helium. So just search online, you'll find that this is the case. So this is something we'll have to take note of as well. So we are coming to the end of the video series. So up till now we have explored how fuel chemistry changes over time due to creation of fission products. We've explored the swelling aspects of fuel, and we know qualitatively that this tends to worsen thermal conductivity. Okay, so we have explored the fuel, we've explored the many aspects, the chemistry, we have explored swelling, etc, etc, and we know that thermal conductivity kind of drops, and this is one of the very important criteria. We have also explored the microstructures as well, and we have also explored neutron damage and what they can do to a reactor pressure vessel. So basically it gets embrittled and it tends to swell as well. So that's all for this video series. It's just to give you an introductory intuition as to what kind of material phenomenon goes on inside a nuclear reactor. Now there are several other phenomena as well. This is not all that's being covered. Other phenomena such as creep and how this is affected by radiation, and how fuel and cladding can interact. Fuel cladding chemical interaction, FCCI. So when fuel and cladding interact, when this swelling gap is closed up, there can be some diffusion can happen, and the cladding can actually become more brittle. And there are other phenomena as well, like eutectic formation during meltdown. So the boron control rod, okay, boron carbide control rod plus iron, that tends to help to liquefy the iron. Okay, but these are just some of the other phenomena that can happen that are not being explored. But with this video series, hopefully it will give you some of the tools and the theory to explore and understand some of the material properties that change and why they change because of radiation and nuclear processes. And hopefully they will help you to understand all these phenomena as well. Thanks for watching. Hope you have enjoyed this video series, and I'll see you around. Bye bye.